everyone. We'll start the room in a few minutes, so thank you for coming. Um, Thank you, everyone. Hi, everyone. Um, Thank you so much for coming. I opened the room a little bit early, but if you want to come up and chat or ask questions, please feel free to either raise your hand or use the room chat. Thank you so much for coming. Hi everyone. Hey Z. Hey David. Thank you so much for being here. This will be really exciting. I'm very excited about this topic. So the whole team will be actually coming today. Um, so um, so it will be Dr. Robert Berman, Dr. Tristan Collins, and Dr. Daniel Persson will be here. So the whole team will be here to present this work. Hi Jamie, how are you today?
Hello, everybody.
So yeah, I put the title. So like the amount of um, words we can use in the title is very limited. So I could only put in Dr. Person's name, but yeah, the whole team will be coming, so that will be really interesting. So Daniel Persson, he's the associate professor at the Division of Algebra and Geometry, Department of Mathematical Sciences at Chalmers University of Technology in Sweden. And Dr. Robert Berman, he's a professor of mathematical sciences also at Chalmers in Sweden. And then Tristan Collins, he's at the Department of Mathematics at MIT, in Cambridge, Massachusetts. So yeah, I opened the room a little bit earlier because they are new to Clubhouse, and so I want to give them a little bit of time. They made their accounts, but just if there's any technical issues that we can figure it out before. And David, yeah, interesting question. You should come up to the stage and ask your question to the guest speakers. They will present their work, but after that, you can ask questions or probably during the time. Hi, how are you? Are you interested in physics or did you study physics?
Hey, Katrina. Morning, everyone. Well, I'm really a fan of Nassim's Haramein work. My background studies were culinary arts, where I found the chemistry as a main bridge to link what the physics of the food means for nutrition and development of health habits. And yes, I found Nassim's Haramein around 10 years ago on his website. He was offering his unified physics course for free. So now it's still online. You can access it. I find it very interesting. But I would like to discuss how this holofractal perspective, what is based on the Planck sphere, means for the unification of what we entangle as new dynamics, mostly for quantum dynamics and quantum computing.
Yeah, that's so interesting that you're in the culinary arts and you're interested, like you learned physics. That's very impressive. Yeah, meet Dr. Daniel Persson. Am I saying your name right? Is it Pearson or Persson? I'm sorry. I'm really dumb. So the microphone button to unmute is all the. Oh,
Yeah,
yeah,
now
perfect. You got
now
it.
I'm unmuted. Yes, hi, nice to meet you. Yes, so I mean, you can just call me Daniel. Otherwise, I usually say Persson in English. Persson.
Persson. Okay, great,
Yeah, yeah,
perfect. Yeah,
yeah,
I'll call you Daniel, but for the introduction,
yeah. That's fine.
for the audience, I will
Yeah,
say your
yeah.
full name. Thanks for
Yes.
coming.
Thanks. Yeah, thanks for the invitation. It took some time to find a suitable date and time where we could all join, but yeah.
Yeah, but it all worked out, and it's worth it. So we have the whole group here. That's amazing. I
Yeah.
love that.
So, I mean, Robert is joining in a few minutes. Tristan will be a little bit late, so he will come in maybe half an hour.
Yeah, yeah, that's good.
Yeah.
He knows the study, so he doesn't need the introduction. Yeah,
Yeah,
he,
that
he
is true.
can he can take care of all the questions for you guys.
Yeah, yeah, that's right. So when he comes, we will just shut off and leave.
Exactly.
Yeah.
Yeah. What time is it in Sweden? It's 6 hours later, right?
It's 5 o'clock now in the afternoon.
Okay. Right. It's been a very long time that I've been to Sweden. I was a teenager. And I was
Ah,
in
Tina.
Denmark and Sweden and
So
Norway.
where were
So
you? Where did you go in Sweden?
uh, we went. We went. So it was as a teenager. I was, and as a kid, I was at the Scouts, not Boy Scouts in Europe. It's just for girls and boys.
Yeah,
You know,
yeah, yeah.
Pathfinder. So we traveled around. So we went to different islands, and then we went. So we traveled around a little bit between Denmark, Norway, and Sweden.
Oh, yeah, yeah.
Uh,
So that's
between
there are many
islands,
beautiful islands outside of this coast here. Yeah.
and then we went to Legoland one
Of
day.
course. Yeah. You have to go to Legoland, right?
Yes, exactly.
Yeah, yeah.
Hi, Robert. How are you?
Thank you so much
The
for joining us,
the
Doctor. It's
let
really
me.
exciting to hear from you. I'm Jamie, and I'll be listening to your presentation as well. Very exciting stuff. I hope I can follow it all.
Yeah, yeah. I hope so too.
Robert, if you would like to unmute to speak, it's all the way on the bottom right hand. There's a little microphone button, and if you click on it, we can hear you if you have
So,
something to say.
so Robert doesn't seem to be on the stage, or
Oh, I see him on the stage.
okay, I don't.
Is
Okay,
it
but
just
maybe
on my side? Could be a glitch.
I'm not seeing him. I'm seeing just you and Jamie and David on the stage, and me.
Yeah.
But
So he's for you. He's in the audience.
I'm not seeing him at all.
Oh, maybe my app is glitching. Jamie, can you see Robert?
I'm seeing Robert here muted.
Okay, okay,
Okay. Oh,
then
Marco
it's fine.
Pettini joined. Do you know Marco Pettini by any chance from Italy? He was a guest speaker. He talked about long distance molecular interaction forces.
No, I don't think so.
No.
No.
Um, yeah, I hope he comes to the stage. He's a really wonderful physicist from Italy.
Mm-hmm.
Very
Nice.
friendly. Yeah. Yeah. I want to test if Robert can hear us. So let me write him a message. because that would be a pity
Ah,
if you cannot.
hi, I found the microphone. You hear me
Oh,
now?
perfect. Yes, now we can hear you.
Okay,
Oh,
it's
there
my
you go.
first time on Clubhouse. Took some time to find the mic.
Welcome, welcome.
Yeah,
Welcome.
it's my second time, so I'm much more experienced than
Yeah,
you
yeah, I will. So I let you take the lead, Daniel.
are.
Lording your experience over your colleagues.
Yeah,
So
yeah.
you just press the microphone and then you just sit back and listen to the other people speaking. It's very nice.
Yeah, it's
So
no
yeah, and how?
video, no need to brush your hair, take a shower.
And then, so how does it work? Anybody can ask a question in just on the fly, or how does it work?
So yeah, it depends on you. So usually people have to raise their hand when they are still in the audience. If they're here, usually people flash their microphones, so to not like interrupt the
Uh-huh.
speaker, they will usually they're muted, like and then to like a signal that they would like to ask something, they would like flash the. If
Uh-huh.
people.
And who will let them in, so to speak?
Oh yeah, Jamie and I, we will do this. You see the screen
Okay,
little
good.
symbol? That means like that we are moderating, so we will
Okay,
see who
good,
will ask
good,
questions. And then
good.
we have the room chat, so people can ask questions there
Okay,
too. So I'll monitor it and then read them if there are questions. So
good.
yeah. Um, so yeah, I think we can start. Um, so I was a little bit distracted to Jamie, can you share the room like on Clubhouse? Yeah,
Sure thing, doing it right now.
thank you so much. I was distracted just chatting. I'm doing that. Okay, cool. So yeah, usually I'll start by introducing you, and then if it's okay, Jamie would ask you like a more general question about how you became to be a scientist. I think for students,
Okay,
and so it's an
okay.
interesting. Yeah.
Yeah, that's
Okay, cool. And then you can introduce your work.
great.
Okay, so welcome everyone to the Science Society. We have a really great guest speakers here today talking about their very interesting research here. We will have basically the team here presenting the work and discussing. So it's a great honor. And let me tell you a little bit of background information. So Dr. Daniel Persson, he's associate professor at the Division of Algebra and Geometry in the Department of Mathematical Science at Chalmers University of Technology in Sweden. And he's a theoretical physicist working on a wide range of topics in string theory, gravity, and gauge theory, and often focusing on problems which lie in the borderline between physics and mathematics. And Dr. Robert Berman, he's a professor in mathematical sciences, also at Chalmers, and he is professor since 2013. And before that, he did his postdoctoral research through Marie Curie and her European Fellowship at the Institute of Fourier, Grenoble, France. And he was also at the Johns Hopkins University. And
No.
oh, is that wrong? Johns
Yeah.
Hopkins
Well,
University,
just
USA.
not really, but never mind.
Oh, I found it on the website.
Really, really, you
Or
should
was it
never
on
trust the
the
web.
repeat?
Don't never trust the web.
Okay, good that you're here to fact check me. I love it.
Yeah.
Yeah, so okay, let's and then later on Dr. Tristan Collins will also join us. He's at the Department of Mathematics at Massachusetts Institute of Technology in Cambridge, and he's there an assistant professor. And yeah, we are very honored to have you here. And if it's okay, Jamie will ask you his questions first.
Thank you very much, Katerina. First of all, thank you very, very much for coming, both of you. It's I was having some look at your papers, quite exciting. I can tell you've given this problem a lot of weight. Boom, boom. Anyway, and my jokes aside, first of all, I'd like to ask Daniel, if you could go first, please. Can you please tell us what is it that brought you into this field of study, and perhaps what got you into science and maybe this topic in particular?
Sure. Thank you for the question. Big question to start. So I guess for me, I really started out wanting to become an astronomer. I was really fascinated by, well, science in general, but I loved pictures of galaxies, and so I wanted to understand the universe. And so I started university basically to become an astronomer, and I took more or less a master in astronomy. But then I gradually shifted to becoming more and more curious as to how things worked at a more fundamental level. So I switched, and then I took a master in theoretical physics. And I really was intrigued by questions like what are the most elementary constituents that build up all matter, and what happened at the Big Bang, and these kind of questions that were really intriguing to me. So I decided to pursue a PhD. So I went to Brussels to do a PhD. And there I started studying basically Einstein's theory of general relativity. So I guess we will come back to that, but just very briefly, Einstein's theory is describing the universe in the large scale structures. And I was studying what happens to Einstein's equations when you try to probe them in regions where they sort of misbehave. So close to singularities, like what happens in a black hole or the Big Bang, and just zooming in there and try to see what kind of structure is it that the equations have when you focus on this. And it turns out that it reveals a lot of really interesting mathematics. So you get new kind of symmetries. And that got me more and more intrigued by this question, that if you ask questions about nature or physics, and somehow it leads you into math, whether you want to or not, you are automatically ending up with some really interesting mathematical structures. And so that's kind of what defined my whole career. I was so intrigued by this borderline between math and physics. Like starting out on one side can get you to new insights on the other side, and vice versa. So in the coming years, I did postdocs and so on. I kept investigating various aspects of gravity, and I became more and more interested in this question of quantum gravity. And I guess this is also something we have to come back to. But I spent many years on string theory, which is a candidate for quantum gravity. And once I got back to Sweden, I came into contact with Robert, and he was there as a mathematician, and we started talking, and we quickly realized that we had some common interests, and we started maybe this project something like 4 or 5 years ago. Just some casual discussions that became more and more intensified, and that's what eventually led to this paper.
So Tristan was actually visiting our department as a postdoc at the time.
Yeah,
that's how we got together.
That's right. Yeah. So that was quick. I mean, we can go into some details later, but maybe that's just for starters.
No, that is a great way to begin. It sounds like your trajectory was always going to bring you to this kind of point here, that your curiosity started as astronomy and just kept on going. That's fascinating.
Yeah, I mean, I like the way you say that. It's kind of funny, when you write applications or where you present things, you're always supposed to present it as if there was this clear trajectory and you were always aiming for this. Of course, in reality, you feel like you're bumping around, and eventually it all works out. But it's interesting that the path somehow looks straight when you look at it when you look back upon it, but that's not always how it feels along the way.
That's why asking these questions have been so fascinating, both for yourself to tell it and for us to hear them, as the background of the speakers here have often been so fascinating.
Mm.
And yourself, Robert, can you please
Well,
tell us?
yeah, so I went off in a completely different direction, I guess. Really excited about philosophy when I was in high school. So I started studying philosophy, theoretical philosophy, actually, because I was really excited about these big pictures. And then I got interested in somehow the philosophy of science when we were studying philosophy. But then I realized that you couldn't really do that if you didn't know the science. That was my impression, at least. And they were very sort of philosophical discussions about quantum mechanics and so forth. But I felt that I really wanted to understand the physics before I started doing any philosophy. So then I actually switched to physics. So I started actually at the physics program. But when you study physics, especially at the time, you actually start with mathematics um, because that's the language of physics, as Daniel pointed out. And then I got hooked with mathematics. So I got really hooked, and it really, I guess, developed into an addiction, you might say. so you know,
But
you
it's
start
a
to
it's a healthy addiction, right?
yeah, you start with some, you inject some basic algebra, and you get to heavier drugs eventually.
Like calculus, or God forbid, differential
Yeah. And then
geometry.
then there is no turning back. I mean, if you so so I got really hooked with math, and but I did study some physics at the side, so to speak. So my degree was also in physics and actually French and literature. But so, and then I got really, I mean, I really wanted to continue doing research in mathematics. So I did a PhD and eventually became a professor. So I spent 1.5 years with my family in France, and before coming back to Sweden. And I guess that's when we met, Daniel. That was probably when I got back, right?
Yeah,
Yeah,
exactly.
yeah. So yeah, and I mean, I've always been. I mean, that's why we have so many things to discuss. Me and Daniel is that I'm really, even though I come more from the mathematics side, I mean, I'm really most excited about the interface with physics, theoretical physics, really. So that's yeah.
That's fascinating. And you even came from a bit more of a philosophical background initially and kind of found yourself into maths and everything else, yeah?
Yeah. So, but it's just that I mean, I really like. I mean, they are for me. It's just really of what I really enjoy is understanding things in general, right? So it doesn't really matter if it's philosophy or mathematics or physics. But what I really then liked about mathematics is that you try to understand something, and in the beginning it's like a completely dark room, but eventually, once you see the light, you can really describe things extremely precisely, and that's what I really appreciated with math. That things are really, I mean, you can really, once you understand, you can make it extremely precise, which I guess is a bit unique for mathematics.
Absolutely. What an incredible way to describe it. Um, Thank you very much. And let's see, Katerina, is there anything else? Or
Yeah,
Katerina?
thank you so much for this great perspective that you shared with us, how the path to science and article like this could be in this work. So thank you. And please start with your introduction of your work. Thank you.
Yeah, so maybe I don't know, Robert. Maybe I can start just
Yeah,
saying a
sure.
little something on. So I mean, this paper that is pinned at the top. I mean, it's quite a technical paper, and I think it makes a lot of sense if we just try to take a big step back and look at where this comes from. So what kind of questions are we addressing? And now we don't really know what the audience is here, so I'm just going to assume that people don't really know so much about what quantum gravity is. I mean, we don't really know what quantum gravity is, so maybe that's fine. So I just tried to paint a little bit of a picture. So there is this, strive for understanding what are the fundamental laws of nature, and that's been ongoing for quite some time. And we now have a very good picture of what's going on, and we certainly know that there are, four, or at least four, but that's we know that there are four fundamental laws that are governing all of the universe. That's what we think. We have the same laws of nature here as in the far distant. And on the large scale structure, we have, as I mentioned, gravity. So the gravitational force is an attractive force that is controlling how masses behave, how they attract each other. So it controls how the Earth moves around the sun. It controls how galaxies behave, the large scale structure. It holds galaxy clusters together, and so on and so forth. But then on the other side, we have the microscopic world. So we have the world of molecules, atoms. And as we just probe into smaller and smaller distances, we end up with what we call elementary particles. So kind of the Lego building blocks of the world. And like the atom is composed of a nucleus, and then we have electrons around it. And so the electron is an elementary particle. And we have then the three forces that are controlling this microscopic world. And one of these, which is perhaps the one that is most familiar, is the electromagnetic force. So that's light. That's what we see all around us. And that's what holds the electron to the nucleus. That's the positive and negative charge, and so on. That's the electromagnetic force. And that's a very strong force. Like compared to gravity, it's really strong. So just think about holding something in your hand. You're easily counteracting the entire weight, the entire pull of the Earth on this. If you're holding a ball in your hand, then the electromagnetic forces holding the molecules together in your hand are counteracting the pull of the Earth on this ball. So the force of gravity is very weak compared to the electromagnetic force. But then if you move further into the nucleus, we have protons and neutrons, and they themselves are made up of even smaller objects called quarks. And then we have what's called the strong nuclear force, and that's holding the nucleus together. So that's the strong nuclear force that is responsible for holding it together. And then we have the fourth force, which is the weak nuclear force. And that's more of a destructive force. It's the one that is responsible for radioactive decay. So it's, I guess, both the blessing and the curse. And so there we have all of the forces that we know. It's gravity on the one hand, and then on the other we have these three forces that are working in the microscopic world.
Yeah.
And just in terms of how we describe these, so we describe gravity extremely accurately using Einstein's theory of general relativity. And it's amazing, like the reason why we have such accurate GPS positioning and so on is because Einstein's theory is so accurate in describing the gravitational force. On the other hand, in the microscopic story, we are using quantum field theory, quantum theory, to describe how all these particles interact. And these theories work amazingly well on their own, where they are supposed to work. So if we want to describe, how to have a satellite that is orbiting Earth and so on, we use Einstein's theory. But if you want to understand how particles collide and so on, we need to use quantum theory.
So Daniel,
yeah.
So maybe we should say something about how you get to the quantum. So maybe I can just mention that. First the electromagnetic. Oops, there's some strain.
There's some disturbance.
I'm
Somebody's
sorry,
singing.
I moved. I moved
Okay.
him. I'm really
Thank you.
sorry. You know,
Okay.
it's a
Okay.
public
Apologies
space.
for that. Yeah. Carry on.
Okay, I go on. Yeah. So maybe I should say first that originally the electromagnetic field that Daniel described, that describes light and so forth, was really described as a field. So you think of it like a field or a wave which goes through space when we send a, I mean, now, for example, when we're communicating over distance, it's an electromagnetic wave going out from my cell phone and reaching, I mean, eventually sort of reaching you somehow. But and that was, yeah. But then in the last century, people realized that you have to be more precise, that these fields are really described by particles as well. So this is the quantum nature. Quantum comes from something, right? And so it's like just this is this description of an electromagnetic wave, sort of as billions of small photons flying through space. And that's the quantum description. It's more precise. It takes into account this particle nature of the force.
Right. And actually, so as a complement to that, why these are so different is also that Robert is mentioning you have this, all these particles that are sort of wave-like, but there are these billions of particles that are working coherently to produce this wave. Now, on the other side, if you look at gravity, so the way Einstein described this, he had this unique insight into sort of unifying what people previously thought of different things. So there's this prime example of space and time. So, before Einstein, people thought of these as separate things. So we are located in a three-dimensional space. So in order to have to, meet someone, you have to decide on an X and a Y and a Z coordinate. And then you have to say that you have to meet at a certain time. And these are separate things. But Einstein, he said that, we shouldn't talk about space and time. We should talk about space-time. So we are really living in some four-dimensional space-time as one concept. And that was the key to his whole theory. And just like Robert was describing this notion of quantum, that also puts the finger on sort of the difference between these theories, because in Einstein's theory, the universe is sort of some kind of smooth, possibly curved space-time. So you can think of, the analog of a surface like a balloon, or you have some just a flat sheet of paper, or a saddle shape, or something else. So that's really what Einstein's theory is producing. It's producing the shape of the space-time around us.
Daniel,
Yep.
let me maybe we should just also mention, I mean, I guess you didn't really mention that, how that works. So you should have this picture in mind that, for example, so how come that the Earth attracts the moon? Sort of, okay, so Newton would say that there is a gravitational pull towards Earth, and then because of the speed of the moon, it goes around, circles around. But Einstein actually said that no, that's not the way it works, or well, he made it more precise, is that heavy, so it curves space and even time around it, so it curves this shape Daniel mentioned called space-time around it, and then the Earth is just like a marble that, it just feels the curvature and just take the closest path in this geometry, this curved geometry, and we go round in this curved geometry. So
Yeah, right, exactly. And if you have this picture, let's say you take this kind of classical example of, you have a bed or a sheet or something, and you put like a bowling ball or something, it will curve the sheet around it, and whatever is trying to move in a straight line around this heavy object will be sort of falling down into the well created by this heavy object. But then you can imagine also, what happens if you drop a heavy, like a stone, in water, right? That you will see waves propagating through just symmetrically outwards in the water. And Einstein's theory actually predicts that you will have a similar type of effect in space-time. So if you have some kind of heavy object, it will create, if this object is moving, it will create waves or ripples that moving out in space-time that we're calling gravitational waves. So that's kind of, sort of analogous to the kind of waves that Robert was mentioning in electromagnetic theory. But the difference is that in gravity, we don't really have this analogous particle notion that we have, let's say, the photon. And that's one of the big questions. Is there some kind of quantum version of gravity where these gravitational waves are really some kind of coherent state of particles that are moving, and it's just because you have many of them that this creates this kind of smooth space-time that we are describing using Einstein's theory. And the question of whether there exists such a quantum version, has many, there are many reasons to look for such a thing, but maybe one can just mention that if you're just looking at the universe as a whole, so we know that the universe is, expanding. We know that the universe becomes bigger and bigger, and so space-time is stretching out. And we even know now that it's not just expanding, but it's accelerating. Maybe we can come back to that. But if you just imagine having something that is expanding and you're wondering, what happened beforehand, so you try to run this movie backwards, well, you naturally end up in a conclusion that it must have been smaller in the past. And, must have been smaller and smaller and smaller. And that's just a naive way of saying that, if you go far enough back in the past, the entire universe was concentrated in a very small volume. And that means that you must have had tremendous gravitational forces, but it's also a very small, tiny volume. So the quantum effects should be extremely high. So there's no way that you could do what we do in our everyday lives of just neglecting. You look at light, we don't really care about the gravitational force if we're interested in how light is working in the lab or in our everyday lives. And the same way, if we build a spaceship and want to travel to Mars, we want to use how gravity works and not care so much about the electromagnetic interactions. But if we try to understand the Big Bang, somehow we expect that there should be, a better theory, a more fundamental theory that involves both quantum theory and general relativity, and they should work side by side. And this is a theory that is somehow replacing or is, more fundamental than what we have today. And this is what we call quantum gravity. So that's what people have been looking for a long time now, what that kind of theory would be like.
Yeah, maybe we should also mention, apart from the Big Bang, that another extreme situation one would like to understand are big black holes. So there is this amazing thing that I'm sure everybody is aware of, that sometimes when a star collapses, it can really sort of implode in such a way that you have a huge concentration of matter in a very small volume, a bit similar to the Big Bang somehow, and that will sort of result in an extreme curvature around this space, around this collapsed star, so that you have this extreme curvature, and it will, if you try to see what's going on from Earth, for example, you will just see a black hole, because it's so heavy that the light which reaches this sort of singularity, as it's called, it cannot reach out again, so it looks completely black from the outside. And then if you want to understand because of the fact that the matter is concentrated in a small volume, if you want to understand what's going on, really describe that physically, you have no choice but combining gravity with quantum theory.
Yeah, right. And maybe as an analogy, I mean, we have, in order to leave the Earth, right, we can't just take any old airplane and just try to go to the moon, because as we go further and further up, eventually, the Earth's gravity will just pull the plane back. And that's because the gravitational pull is strong enough to hold you down. And in order to counteract that, you need a rocket that is sufficiently powerful so that it can accelerate beyond the acceleration that is pulling you down. And so a black hole is simply, but it's an event or an object where the gravitational pull is so strong that not even, even if you can travel at the speed of light, it's not sufficient to escape the gravity. And it's exactly at that threshold when you say that you have a black hole, because not even light can escape.
Yeah. Okay. Shall I say something about how, I mean, the sort of approach we're working on to sort of describe quantum gravity?
Yes.
So Daniel described these two kind of forces. You have gravity on the one hand, and then the other forces, which are the microscopic forces like electromagnetism and so forth. And they are actually so. I mean, gravity is described sort of in this idea as the curvature of space-time, and then there is a rather different. So that's a bit technical, so I will not try to explain the concept of a gauge theory. But the important thing is that basically in a gauge theory, there is a parameter called the rank, which for these three forces is 1, 2, and 3. That's all you need to know about gauge theory, is that there is this parameter, the rank. And for the electromagnetic force, it's 1, and that's because there is just one particle, the electron. And then for the electroweak force, I mean the weak nuclear force, and then up to the strong nuclear force, then this number is n equal to 3, and the 3 here is the number of quarks. There are just 3 quarks, and you can combine them together, and you get the composed particle, which is the proton, for example. So the proton is made of a maximal number of quarks. So that's all you need to know about gauge theory, that there is this number, n. So, and then you look at it, and that looks a bit, does nature just take advantages of 1, 2, and 3? What about 4, n equal to 4, 5, 6, 1 billion? I mean, is there a physics corresponding to those theories? And this sort of is really what, in the 90s, an answer to this was provided by Juan Maldacena, which is really the starting point. And he said, if you take this n to be close to infinity, you take it larger and larger and larger, what will happen is that gravity will emerge. That's basically what he discovered. So another way to say this is that, okay, so maybe gravity is not so different of each theories. 1, 2, and 3, and you get 3 quarks. But then if you sort of look at a similar theory, and you take this number larger and larger, it's like you have these sort of virtual, I mean, you can think of these quark-like objects, you get more and more of them, and when you compose them, maybe you really get space-time. That's one way to think about it. What do you think, David? Does it make? Can we explain it that way?
Yeah, I mean, So maybe just before going on, I just noticed that Tristan has appeared, so maybe we should invite him in to present himself.
Welcome,
Yeah,
Tristan.
welcome, Tristan. He wrote me that he needs to.
Oh, there you go. Okay.
Hi, Tristan.
Okay. I'm here. Okay. Sorry for delay.
So glad you
Can
could
you
join us. Thank you for coming.
can you hear me? Can you hear me? Okay.
Yes,
Does it
we can.
sound okay?
Yeah.
Okay. Great.
Yeah.
Yeah, so basically, we just started by giving a brief introduction, Tristan, of what we've been doing. So maybe we just continue, and you can, chip in wherever you feel like.
Sure, sure. Yep.
Yeah, yeah. So I was so Daniel first explained that I mean this sort of this core theory that we have gravity on one hand, which is the sort of microscopic force, and then the microscopic forces. And I said now that there is this technical term gauge theory, which describes the microscopic world, and it goes from 1, 2, and 3. That's the three different forces, because you have this fundamental parameter n equal 1, 2, 3. 3 is the number of quarks. And then there was this new development in the 90s by Juan Maldacena that basically he answered the question, what happens if you take this number larger and larger? What kind of physical theory do you get? You get theory with like billions and billions of quarks. And that theory, actually, when this number n tends to infinity, somehow what you should see is that gravity emerges. That's one way of describing it in non-technical terms, I think, what he did. And that's a starting point for our paper. But one should say one more thing. So, or actually more a lot of things. But okay, so there's one. Okay, so first you say, okay, then we can all go home. I mean, this is all solved, right? So because, well, it's the devil is of course in the details, because I mean there are catches here. So one catch uh, is that uh, is that when you do this, you have a gauge theory, and you try to you see if gravity emerges. You do this gauge theory with n equal to 4, 5, 6, and infinitely large, and you should see gravity emerges. First of all, what happens is that gravity actually emerges in a space with an extra dimension. So you go, even if your original theory was in space-time, the gravity emerges in a 5-dimensional space. So you get sort of emergence of an extra dimension. Okay, and that's concept of the holographic principle that we could come back to later.
But maybe, Robert, this is a good place to say something about its relation to black holes. I
Yeah,
mean,
good.
so we have. I mean, in the title here, I see that Katarina has written "How Gravity Emerges: The Holographic
Okay,
Principle."
yeah.
And I mean, there is a precursor to like this story of Maldacena and so on. In some sense, the Maldacena theory that Robert was describing is like a very specific realization of what is called the holographic principle. And maybe the simplest setting to explain where this comes from is that when you look at black holes, there are many things that we don't understand, but the first thing we explained was that black holes are supposed to be black, but in turns out that they're not really expected to be entirely black, and so this was discovered by Stephen Hawking and David Bekenstein many years ago, and they're actually expected to radiate. So this is what is called Hawking radiation, and it's this sort of surprising effect of trying to use some quantum theory just at the boundary of the black hole. So they were analyzing, what happens if you have a situation where a particle, and so we can't really go into this, but what can happen is you can have a particle and it's sort of dual, it's anti-particle with a negative mass. That part with the opposite charge, it can be created and disintegrated in a very short period of time in empty space. And if this happens just at the boundary of a black hole, an antiparticle could in principle move into the black hole and the particle escapes. And effectively what happens is that it will reduce the mass of the black hole, and the particle that escapes will be sort of radiating out. And the expectation is that somehow this radiation contains information about what happens inside the black hole. But they could also calculate the so-called entropy of the black hole, or the fact that it has a temperature. So just like we have, in a room, we have lots of molecules that are moving around. And we are describing them using the macroscopic notion of a temperature rather than just saying, whichever each molecule is moving in this and that direction with this and that velocity. It's kind of inconvenient. So we're talking about this temperature. And you can talk about the temperature of the black hole because it's radiating. So it behaves a lot like an ordinary body that is radiating. But the surprising thing is that if you have an ordinary matter system, the temperature or the entropy is related to the volume, like the particles live in some volume. But for a black hole, somehow the information about the entropy or the temperature is contained only on the surface of the black hole. So if the black hole is three-dimensional, somehow all this information is just contained on the boundary. And that's exactly the kind of holographic relation that somehow it seems that when you're dealing with quantum gravity, there is some kind of holographic principle that the information contained inside is somehow projected onto the boundary. And there, it's like the opposite of what Robert was saying. Imagine if you have, you're at the boundary, then somehow when you want to understand what's going on inside, it is like an extra dimension is emerging. So that's specific for black holes. But what Robert was saying is that, people have taken this idea one step further and said, maybe if the entire universe somehow there is a holographic description of the universe.
Yeah. So maybe one way to say it as well is that there are situations that we are familiar with. I don't know if I can come up with something that where we can have two different descriptions of the same phenomenon, right? So this is and we talk about the notion of duality. It's like we have two different descriptions. But they are dual. They are basically equivalent somehow. And this is an instance of a duality, is that you have one description which is somehow valid horizon. It's like the description if you would take if you would be so brave with a rocket inside the black hole, and you would go, you would pass the horizon, but you wouldn't even notice anything is special at that point. You would just go on. And eventually you would get into trouble when you reach the singularity. But you would describe physics in this sort of in three space dimension of time. That's the way you would describe physics. But then from the out, you see this rocket. Eventually, when it reaches the horizon, something really weird happens, and it looks really weird because the lights get distorted. But then eventually, you cannot describe what's going on inside the horizon. So your description from the outside would just be a description taking into account the two dimensions living at the boundary of this horizon. So somehow this would be like two dual descriptions of the same physics. One three-dimensional space inside the horizon, and one from the outside, which describes everything in terms of this two-dimensional surface.
So maybe I can give my very simplistic elevator pitch for this ADS-CFT thing, which has nothing to do with physics. But so imagine that the universe is a soup can, and on the boundary of the soup can there's a label, and the label contains some list of ingredients, and in the interior of the soup can there's soup. And so ADS-CFT, this kind of holographic principle, is saying that if you know the information on the outside of the soup can, which is the list of ingredients, then you should be able to reconstruct the soup which is inside the can.
So maybe we should say there is this technical word ADS-CFT, but another way to say it, just to remember it, is this gauge-gravity duality. So in this kind of duality for gravity that Maldacena discovered, it's a duality in the sense that the description of gravity is in terms of a different language, which is a language involved. That's like the ingredients. It's like the gauge theory, that they are the ingredients to form gravity in your picture, Tristan, I guess. Right?
Yeah, that's right.
Yeah, maybe one should also say that, in this language of gauge gravity, what is really is a two-way duality. So we've now been focusing, maybe we want to understand something about gravity like black holes, then perhaps there is another description that is hopefully simpler in terms of some gauge theory, some quantum theory, where you don't really have gravity, but you have a different setting. But this kind of duality also goes both ways. So in principle, you can look at situations where you have difficult questions in quantum theory, or where the quantum theory is strongly coupled, the gauge theory is strongly coupled, as we say, and then you can go to the other side, and that's actually where the gravity situation is simpler, and you can try to answer questions about the quantum system using gravity instead. So it really goes both ways, and you can look at. So people have really looked at this from different perspectives, and there is a lot of interest in understanding complicated matter systems from this other perspective using gravity.
Yeah. And I think the picture to have in mind is really, because it's very confusing that how can one theory in, for example, 2 dimension describe a theory in 3 dimensions? But the way to think about it, I think, is that you should visualize this horizon of a black hole, and the inside, we don't see it from the outside, but it's really some gravity theory in 3 space dimensions. But the way we describe it is using gauge theory, which really is localized on the surface. And so the gauge theory is in 2 dimensions, space dimensions, and the gravity is in 3 dimensions. But there is no contradictions in the sense that, how can 3 dimensions be described by 2 dimensions? It's like something should be missing. But the answer is that, well, we're not describing gravity in 3 dimensions with gravity in 2 dimensions. We're describing gravity in 3 dimensions with gauge theory in 2 dimensions, and the gauge here gives you the extra information needing somehow. The description is different.
Yeah. So I guess we've been talking now for almost 50 minutes. Maybe it's a good time to just stop and see, are there any questions? Do you want us to just go on? And we can probably talk for 4 hours about this.
Okay, or maybe I should just say 2 minutes about what we added to this picture.
Okay. Yes. Good.
Yeah. So what we added is that so you have the going back and forth between dimensions. So that's one thing. But one should also say that the gravity that Maldacena described also has some extra structure. It's what is called supersymmetric. And so that it has some extra symmetry that for the moment has not been measured in the world as we know it. So it's somehow it's still in theoretical physics many people still hope that supersymmetry is really part of the fundamental theory describing the world at the fundamental level. But anyhow, so he assumed he needed this supersymmetry to make everything work technically. But then he actually also assumed that there was a maximal amount of symmetry, of supersymmetry. So our starting point was that, okay, can we describe gravity, a supersymmetric gravity, but with a minimal amount of symmetry? And that's a well-defined sort of, theoretical physics problem that you can formulate in some mathematical terms. And in some sense, we tested this duality for this situation, and it worked out well, you could say.
Yeah. So Katarina and Jamie, should we go on, or do you think there are questions?
Yeah, let me check and ask people. I know that Tristan already answered a few questions in the chat. Thank you for that, Tristan. It's a wonderful description. Please, if you have any questions, raise your hands or flash the microphone to let us know that you have a question. If not, I'll ask my very dumb question. If that's okay. I don't know. I'm not a physicist at all. I did some physics training at some point, but so when I think of, because of the holographic principle that was referred to, or I referred to, when I think of holographic is that as far as I know, in each pixel, basically, you have a very simplified description of the whole picture, basically, right? Is that correct? Like in a regular hologram. So with the soup, with the can and the soup description, you have basically not is it an outer layer basically that has, let's say you would only have the surface of a brain information, but with that information you could basically reconstruct the whole brain or whole organism just based on the surface information. Is that the correct way to see it?
Yeah.
And so you added now basically that you don't just have, as you said, like all the ingredients, but also the recipe, like how to come up with this exact universe model and not just some universe model with the same ingredients. Is that correct?
Well, I think maybe in this analogy, on the surface of the soup can, you're told that in the soup there's, I don't know, water and carrots and peas and chicken and I don't know what kind of soup you want to have inside the can. But anyways, you're told that there's some list of ingredients, but what you're not told is how you're supposed to take those ingredients and reconstruct the soup. And of course, in this case, we're cooking something that we've never cooked before, so we don't even know what kind of techniques you're allowed to use. Maybe you're supposed to bury it 6 feet underground and drive over it 3 times with a car or something like that. I mean, who knows? So somehow I think the point of, or one of the sort of contributions of our work is to say, this is exactly how you take these ingredients and recombine them in order to get gravity out on the other side. So we give, in some sense, a recipe for where gravity should come from.
Yeah.
So maybe one can, yeah, sorry, Robert.
Well, so it's a precise recipe, but it's also, I mean, it's actually several. I mean, the scope it gives, because the first model, this symmetric model, is gravity in a very sort of symmetric landscape, so to speak. And so we somehow also extended the scope to describe less symmetric landscapes, if you want.
But maybe one could just say a little something on, what is this soup? So I mean, what we're trying to do is describe, how you get gravity out of some alternative description. And what we mean by that is basically that we want to be able to reproduce solutions of Einstein's theory from some alternate quantum system. And what are solutions to Einstein's theory? Well, that's, as we talked about before, that's really geometries. So that's solutions correspond to different shapes. Even if there's space-time and that's difficult to imagine, you can just imagine, either it's a sphere, for instance, it's a balloon-like shape, or if it's a saddle-like shape, or if it's just flat shape, or something else. And what we're trying to do is really show how this shape is emerging from another setting. And I mean, I like to have this idea of this children's drawings the kids have when they have just a lot of dots, and they have some instructions for how to draw lines between the dots. And once you complete the whole thing, you see that, oh, this is a duck or something like that. And that's kind of how this picture, it's emerging from some other set of rules. And that's the kind of emergence of gravity that we're looking for.
Yeah, so that's a good point. And really, so the way to think about this maximal supersymmetry that Maldacena originally considered, that's like a sphere. It's a perfect homogeneous. But then you wonder, I mean, can we describe, I mean, more general shapes that are not perfectly symmetric and so forth? So, and people certainly expected this to be true, but we made it precise. We really, in some sense, mathematically proved that yes, I mean, as Daniel said, you can connect the dots and get any shape, more or less.
And you also have these shapes in a vacuum state, and that would basically explain the dark energy. That explains then the expansions of the universe. Is that also correct, or am I misunderstanding? So in the vacuum, you also have the geometric shapes, right?
Yes. So I think it's a stretch to say that it explains dark
Yeah,
energy.
it's a big
Maybe just
stretch.
briefly, like, so what is dark energy? So I mean, we have this universe, and let's just assume that the universe is like a balloon, and it's just the surface of the balloon, and we have like each cluster of galaxy is like a little coin that we glue onto the surface of the balloon, and then we're just the balloon is blown up, and so you get each little coin is of course held together, right? It's not becoming bigger, but the distance between the coins is growing, and that's like our universe. The space-time becomes larger. Each galaxy is held together by gravity, but the distance between galaxies or galaxy clusters is growing. And until recently, I mean, I gave courses on Einstein's theory several years ago, and then we were always explaining to students that we don't really know, if there is sufficient amount of matter in the universe, then eventually the expansion will slow down, and maybe it will even contract, and we will have some kind of big crunch. We wouldn't know. But I mean, now we do know that this will most likely not happen, because the universe actually started accelerating. And so roughly around 2/3 or something around the age of the universe, something caused the expansion to speed up. So something is counteracting the pull of gravity and is causing the expansion of the universe to accelerate. And that something is what we call dark energy. And we don't really know what that is. But one thing that we usually say is that somehow an energy, a vacuum energy, a fluctuation in the vacuum is causing this, although we don't really know how that works.
Yeah. So one should maybe also say that, so this one way to think about it is that originally we described the theory, Einstein theory of gravity, as you would start with a flat space, and then once you put some matter inside, like this bowling ball, it will curve space around it. So it sounds that you would need matter to curve space. But then, Einstein later discovered, that's what he called his biggest mistake ever, by the way, but that there is, that even if there is no matter in space, maybe the universe is somehow homogeneously curved anyway but the same way at all places, and that this is the dark energy. It's playing the role of the matter, which goes all the way through space, right?
Yeah. So I think, yeah. So it's not the case that we are really describing what dark matter, what dark energy is, but certainly, as you have a theory that can describe how gravity emerges, you can certainly start asking more and more complicated questions. And
Yeah.
yeah.
And if I could ask a quick question, please.
Yeah, go ahead.
So there's a lot of information you've given me, so my head's all spinning. So please correct me if I'm misinterpreting what you've said, okay? But when you described like black holes, and you described as well that you're not trying to describe how would you put it, like a two-dimensional model and then making a three-dimensional model from the two-dimensional. You're not coming from that direction. You're more theorizing essentially of a 3D model where we don't really understand yet, but you're saying that this 3D model could explain our 2D universe that we're currently living in. And I know, yeah, is that kind of correct, what you're saying?
So I'm not sure. I'm not. It's not entirely correct. So I would say that at the moment what we, as far as we know, we live in a four-dimensional universe, right? But that's not. There are several ways in which you could imagine having more dimensions. But one is you could in principle have a situation where there are more dimensions that we're not seeing, but they are very small. So you could imagine having a water hose, and you have a little insect like an ant walking on the water hose. Now, if you're looking at this water hose from a distance, you would just see that this is a one-dimensional line. But if you're a little ant, you could walk around the water hose, so the ant would know that this is really a two-dimensional situation and not the one-dimensional situation. So the ant would need to specify two directions to meet with another ant, right? And so this is something we don't really know. In principle, it could happen that if you would just be sufficiently small, there could in principle be extra dimensions that we are not seeing.
Right. So,
But on the other hand, you could also have a situation where the extra dimensions are large and we are somehow confined in a four-dimensional slice in a bigger universe, and we just cannot leave this slice, and so we're not seeing them. So these are basically, both of these concepts actually occur in this Maldacena theory that we are discussing. So I'm not entirely sure which of these you were asking about. I just wanted to.
Yeah, maybe I can add something. So if I understand the question, I think I think what is challenging is to look around. I mean, I guess what you're trying to do is to look around us. We see the world. There is gravity. How is it described by this gauge theory, in this Maldacena framework? And that's rather tricky to explain. So maybe it's even better to think of a black hole. And then the goal is really to describe what's going on inside the horizon. So it's like you have these, you've probably seen these amazing pictures of black holes, like a black disk. And we know that there should be a way to describe what's going on inside. And what's going on inside is really going on in four-dimensional space-time. I mean, three-dimensional space. That's what, I mean, there are things going on inside, we believe. But we cannot probe that from the outside. So basically in this framework, one tries to understand what's going on inside the black hole only by using a theory which basically lives on the boundary, on this horizon, like just before you go through the horizon. A theory which is really just using instructions, as Tristan said, in terms of the surface. So this is, I think that's the easiest way to visualize the difference between the dimensions.
But maybe one thing we should be, I mean, I don't know if it's obvious, but I mean, Robert was before talking about these symmetries, and we're looking at theories with a lot of symmetries. So at the moment, the work we have done is not really, explaining anything about the world that we're seeing around us, at least not as far as we know. We are really looking at this problem, which is an important problem that we want to understand, and then we are looking at it in sort of, if you want, it's a toy model. It's a model with more symmetries than what we expect to see around us. So, I mean, we have very good evidence that there is a supermassive black hole at the center of our Milky Way, and we are not really, attempting to describe that black hole. We are saying that, black holes exist in Einstein's theory. Any gravitational theory could have black holes. And we are trying to address this question of the emergence of gravity in this simplified toy model that we are looking at.
Yeah, it's like this joke of physicists trying to describe a cow with a sphere, right?
Yeah, exactly.
The spherical cow.
Yes.
So to a first approximation, a cow is just a sphere.
Yes.
So that's our approximation, basically. Or it's slightly better because it's not even a sphere. It's something less symmetrical than a sphere.
Yeah.
Right. And one last question for you here is, can you please explain a little bit what, because it sounds quite mind-bending, but what are antiparticles, and are they like very important to your kind of quest here? to kind of look at what you're working on? Because it sounds to me that you're working on a kind of unified theory, right? Where Einstein's theory can connect with was it general quantum theory? Is that right?
Yes, right. So,
Yeah.
so when you're, I mean, according to the way we understand the laws of physics, the particles that we see around us, the way we understand them in quantum theory is in terms of describing basically, roughly their symmetries. So we can talk about what kind of symmetries they have, and it's a little bit hard to visualize, but electrons and photons and so on, they have different types of symmetries. And when we try to classify all particles, we see that it's very natural that you also have sort of opposite to each particle. There is like an anti-version that has a negative mass, and if you would put them together, they would just annihilate each other. So
Daniel, maybe I should
negative energy.
Maybe I should add, I mean, this is a beautiful instance of this interaction between mathematics and physics, because basically what happened was that Dirac wrote down the equation for example, for the electron. And so the equation, I mean, he looked at it and he tried to solve it, and one solution was obviously the electron, because the equation was made to describe the electron. But then he said, hold on, there's another solution. Every time I have a solution, I have another solution. Who's this guy? And that happened to be the antiparticle, which was later discovered.
Yeah, exactly. And somehow it seems that in the very early universe you would some kind of something happened that caused that somehow we have basically an abundance of particles and not antiparticles today. So we have some kind of breaking of the symmetry between particles and antiparticles have happened, but antiparticles are still created in particle accelerators. When you smash particles into each other, you can have creation of antiparticles. And as we mentioned before, you can have this situation where, like in vacuum, it's allowed for particles and antiparticles to spontaneously be created and disintegrated in very small time frames.
Okay, thank you very much. That's fascinating. Okay, you can continue.
So maybe I just remember something. Maybe I can just briefly add that as well. There is this book by what's his name that wrote Help Me Out, the Mona Lisa story. Anyway, don't Robert Langdon is this.
I know who it was.
Dan Brown.
Yeah, Dan Brown.
Yeah. He wrote this book about some physicists discovering a way to contain antiparticles in some cylinder, and some people stole it and it would create a bomb or something. So that's not really.
But I guess, Daniel, correct me if I'm wrong. I mean, it is something of a mystery why. That's what you were trying to explain, that why we see so much matter in the universe, but not so much antimatter, right?
Right, exactly. So, and I think that's like we had this theory of quantum gravity, some more fundamental theory in the early universe, but something caused this kind of breaking of the symmetry, and we don't really know.
Yeah, and it's also somehow illustrating this procedure we have of doing theoretical physics, that we really, I mean, ideally we would like to describe the world around us, like the cow on the grass that I was mentioning. Ideally, our theories should describe everything fundamentally all the way up to the cow and even further, I guess. But there's no way we can do that because it's just too complicated. So what you do in theoretical physics is that you look at these toy models, which are simplified symmetrical situations, and in such a situation, typically you would have as much matter as antimatter. And then the next step, once you understand that, is to explain why symmetry is broken, so why the world is more complicated. But that's the next step, which is very challenging.
Yeah.
That even brings up more questions, but please continue with your talk. Thank you.
I mean, one thing that it might be interesting is that, I mean, at the moment now we're talking, and it sounds we are very synchronized and so on. But I mean, in reality, when we talk, I mean, it's quite fascinating if you would like physicists and mathematicians, that very often there is this really interesting language barrier that maybe both are using mathematics but in different ways. So a lot of the times when we started this collaboration and so on, it's a lot also just translating, like, look, I have this statement in physics and discussing with Robert and Tristan. It's like, oh, in mathematics we have this, and then suddenly you're realizing that you're talking about the same thing in different ways, and just that realization alone can be a really interesting discovery.
I mean, there is this amazing story. I mean, we mentioned gauge theories, which is this really the language to describe the electromagnetic field and all the forces except gravity. But that was discovered independently, actually first, I guess, or well, at the same time in mathematics, and then in physics. And the funny thing is that, so in mathematics was Chern, and in physics was Young and Mills. And the story, I think, is that Chern and Young would even have lunch together once in a while, I think, but they never realized that they were talking about the same things. So yeah, it's amazing.
That's so interesting. Did you, by any chance, read about Enrico Rinaldi's work about using quantum computing to simulate black holes and deep learning? We had him as guest speaker here. The paper was published like in February this year.
You're not talking about there is a woman in the US doing simulations like this in her lab? That's not who you're talking about? I don't remember her name.
No, this is in Japan at the recent, but no, but yeah, anyways, I was just interested how you think, because he also has a holographic setup.
Okay, so I think well, I guess it's Daniel mentioned that, I mean, once you have system, you can try to make this duality, very general, and say maybe for quite general quantum systems, when we describe them and we put more and more particles together, maybe some geometry emerges. So I guess that I know what paper you're talking about is that maybe you can even describe a black hole, something looking like a black hole in a lab using an appropriate quantum system, maybe.
Yeah, it's a model universe. I can share in the chat the paper. It's a very simple form of a universe model.
Right. Yeah. But that's, I guess that's why, the way science proceeds again is that you want to simplify, you want to describe a complicated, you try some characteristics. You come up with a toy model which has some of the characteristics of this model, of this phenomenon you're trying to describe, and you're hoping to understand your toy model first. So that makes sense. I think I'm sure people are trying to do this at home.
Yeah, maybe just to add briefly to this, I don't know. I also don't know exactly the paper, but there is this general story surrounding black holes involving like information loss and so on. So, people have debated, what happens when you throw in a bike into a black hole. Is the information about this bicycle lost? And according to the laws of physics and information theory, we wouldn't expect that information would be lost. And there was this famous bet, Hawking made a bet, someone that, information is lost. And I guess it was Susskind, right? And so there's this question, in Hawking radiation, for instance, is there a way of doing what Tristan was saying, reproducing the soup and so on? Is the information lost, or is it somehow there? And this story has developed a lot, and people are trying to understand this from the quantum information point of view and so on. So I don't know if that's
and I guess related. To some extent, I guess that Hawking eventually admitted that the information is not lost because of this gauge gravity duality. Right?
Exactly.
Because we have this dual description using a gauge theory, nothing is lost. Even inside the horizon, things are going on, but we can describe it from the outside using gauge theory.
Yeah.
So in some sense, I guess the paradox was resolved, but then, I mean, people are looking at much finer questions like how would we ever reconstruct I mean, even if we know that in principle there is a dual theory, gravity, I mean, how can we actually use it to reconstruct the information? I mean, that's an extremely deep question.
That's interesting. Yeah, so I was looking back at it. So it doesn't really matter, but he tried to create a useful quantum computing and deep learning model to study dynamics of matrix quantum mechanics. I posted it in the chat.
Yeah. Okay, I'll have a look. I remember seeing this paper, I think, at some point, but yes, I guess the one difference between, maybe that's worth pointing out. So if I remember that paper, I don't have it in front of me, but that the point is that once you write down some quantum system, you can try to simulate it with a computer, basically. But what we did, which is different, is that we, instead of using computers to simulate a system, which you could basically do as well, we actually just used, mathematics to instead of doing the experiment on a computer, you can actually use mathematics to see what the end result will be. So
yeah, it's interesting. It's interesting if you all come up with similar results or very different ones. It should be the same, but well, depends on
I'm
how
sure
good
it's
his
related.
model is, right? But and I have a question that is probably a little bit unrelated. So, based on your model, can you make assumptions on if the universe is deterministic or not? Because I know that Einstein had also a quite a fixed idea about that. So, is there, based on your model or calculations, what is so with the ingredients and the can and the soup can, like, is
No, I
the
think
outcome? Yeah, go on.
no, I would say that no, we don't have anything to add because we really use the language of quantum theory to describe gravity, and quantum theory in some sense is not deterministic, even if people debate over that. But we don't, I wouldn't say that we add anything. We just say that we can use quantum mechanics in some sense to do this, but I guess that's a completely different discussion. I would say, what do you think, Daniel and Tristan?
Yeah, I completely agree. I mean, the whole point of this quantum gravity question and what we are doing is that we are saying that there is a way to describe gravity using a quantum system, but it's basically looking at ordinary quantum system in a different dimension that is containing information about gravity, but we're not really changing anything about quantum theory itself.
Okay, great. Yeah, makes me. Okay, yeah, Tristan, go ahead.
Sorry, I was just going to. Yeah, I agree with what Daniel and Robert said. I don't think we're trying to update quantum theory.
So coming back to my life story, that's why I switched to from philosophy and physics. These questions are too hard. These about determinism and stuff. It's just too hard.
Well,
Yeah.
we actually had scientist Max Planck here on Friday. He looked at the maximal entangled inner proton, and he did experiments about that, and he says that based on his experiments results, it's not deterministic, which made me very
Really?
happy.
Okay.
Interesting.
Okay. Good to hear. It's settled then. Good.
It's settled.
I
Okay.
agree.
Then we don't have to discuss that ever again.
I'm pleased.
Yes, I can share that paper. It made me very happy. That's why I invited him, basically. Anyway, if anyone else has questions, Dr. Shah, yeah, please go ahead.
Yes, I have a question and thank you so much. I was a little bit late, but for sure I will listen to the reply. My question is about the beta deformation, which you mentioned about that it just happened when the actually fractional. You just explained about the power of the Slater determinant. And when it's happened, it was a negative and fractional power. So my question, is that the same as microstate in a black hole? Because microstates happen when the gravity is weak, or at least it happened in a situation when we have a weak gravity. Would you please explain a little bit more about beta deformation?
Okay, I mean, I could say something. So this is very technical. So yeah. So I can only say this in a framework for specialists, I guess. But I think the way to think about it is that what you're talking about is that we write down a very specific quantum state. So that's the recipe that Tristan mentioned. And this very specific quantum state, as you say, technically is described by a negative fractional power of a more familiar object, which is called a Slater determinant. So then so why this negative fractional power? And the answer is actually in some sense very simple. So this is the natural which respects all the symmetries of the theory, like technically conformal symmetry and supersymmetry. So it's just the simplest thing you can write down, which respects the symmetries. And then how to interpret that in terms of microstates, I don't know, actually. That's an open question, I would say.
Yeah, I completely agree. I don't think we really understand. I mean, one can say maybe that, so we have this prescription, or as Robert said, so we have this specific state that we describe mathematically in terms of this determinant, and using that we can show how this gravitational solution emerges. And then of course you can ask the question, what kind of physical, is there some kind of interpretation of the state itself in terms of physics? Is there some kind of natural way of describing what kind of particles it represents? And I guess that's something that we're hoping to come back to, but at the moment we don't really know. We think it's related to something called giant gravitons, but we didn't really go into that in detail in the paper. But what we have now is sort of a first prescription for how to do this, and there are many questions one can pursue in terms of getting more and more details as to what this means.
Yeah.
So it's not in a coherent state, right?
Well, it is in some sense. So okay. So this will get technical, but so I guess maybe that's even Daniel and Tristan in the first version of the paper on archives. I mean, there is a discussion about right, about
yes, that is
so
true.
that's a place if you want to have a look technically in the first version on the archives, because basically, I mean, there is a connection to coherent states. So basically, it's just there is this remarkable phenomenon that because of this negative power, what happens is that, I mean, when you form this state, it's like a state of n dual giant gravitons, technically, like you can think of this like the gravitons of space-time. But then, because of this negative sign, the state will be localized at specific regions of space, and these will be some branes from the point of view of string theory. So they are dual to the original branes somehow. So you can think of it as a coherent state of supergravity branes, technically.
Yeah, I got the answer. It's a supergravity. So that was the answer.
Yeah.
I have a question. Speaking of information and information theory, what does a physicist mean by information? I mean, how do you quantify information? What is a unit of information?
Good question. I'm not sure I want to try to answer that. Do you have some good answer, Tristan or Robert?
One bit.
One bit.
Yeah.
One
So
bit. Yeah.
it's well, it's an extremely general question, but I mean, in some sense, I mean, very in popular terms, I mean, it's this the sort of the minimal ingredients of the recipe somehow. That's the bits of information.
I mean, the point of quantum information theory, I guess, is to sort of go away from having just 0 or 1 turned on or off. You can use sort of the spin of a particle, and then you can have more complicated situations. So that takes you into quantum information theory. But I'm not sure we are really qualified to discuss that.
Yeah, no, but it's the sort of simplest ingredients in a description. That would be the fundamental units of information. And in quantum theory, it could be like, as you say, spin directions.
Okay, thank you.
I have a question that kind of steers us a little bit away slightly, but let's see if it's relevant enough. With you working on this quantum gravity idea, right? You are kind of unifying Einstein with the quantum, like you said. And you mentioned the 4 different forces of the universe, or at least 4 that we can kind of talk about just now. Do you actually suspect there is like larger laws at play that are like encompassing all of these in some kind of larger way?
I mean, yeah. I mean, one can say certainly we are, throughout the history of development of the theoretical physics, the laws of nature as we know them, we have seen several situations where we have unification. So I mean, one of these I mentioned before, space and time into space-time, and then we have this famous example of Maxwell's equations that previously, before Maxwell, people thought that electricity and magnetism were 2 separate phenomena, and then Maxwell showed that in fact the electricity and magnetism are just 2 sides of the same coin, which is electromagnetism. So it's just one force, one phenomenon. And in what is exactly what we see, that today we seem to have gravity and we seem to have all these different forces, and they have very different strengths. But as we sort of wind the tape backwards, there are unifications happening. So the strength of the forces, they become closer and closer. So we talk about unification of electromagnetism and the weak force. So that's called the electroweak force, and that was awarded a Nobel Prize. And that's where these forces sort of unify into one force, if you want. And that's described by a quantum theory called electroweak theory. And so people always expected that you can keep doing that and go further and further back in time, or to higher and higher energy scales, and the forces would sort of unify.
Yeah, and also, especially if the world is supersymmetric, then it works
Especially
perfectly well.
if the
It's
world is
just like
supersymmetric.
on the spot. I mean,
Yeah. And so this is a beautiful idea, and it's one that we don't really know exactly how it's realized, but certainly there is this idea that the very early universe is described by a much more symmetric theory, where you more or less have sort of one force, or it's all described with the same framework. And then somehow something happened that caused these phase transitions. The universe started expanding, it started cooling down, and the forces separated from each other. And then we end up in this state where we are today, where we have these different forces.
Yeah.
So
so that just maybe one could add, I mean, one can also, I mean, this gauge gravity duality, at least in the way I think about it, it gives some sort of unification, because it really says that gravity is not so different after all. Also, gravity is described by by a gauge theory. So you could say that all the forces are unified in this picture by a gauge theory, even though you need different gauge theories. That's the non-unification part.
Yeah, right.
Yeah.
That's absolutely fascinating. So, like the idea that as the universe was growing and expanding, like the laws that created it are like splintering off, and we're discovering the splinters.
Yeah,
And
yeah,
yeah,
that's right.
yeah. It's
that's
it's amazing.
that's
It's I
incredible.
mean, the way I have this way somehow. It's a bit like one. I mean, so this is related to this famous anthropic principle, but you could also somehow maybe the reason that we shouldn't be too surprised that we live in a world where the forces look different, because if they didn't, there wouldn't be any intelligent life to observe it somehow. We came into the game at the right time. Otherwise, we wouldn't be able to develop capacity to understand the universe.
Yeah, it's good that the symmetry was broken, right?
Yeah. Otherwise, the universe would be too boring to intelligent life, I guess.
Exactly. Yeah.
Wasn't it Carl Sagan? And I'm going to misquote him terribly, I'm sure right now, but he said something like consciousness was the universe's way of observing itself, or something like that.
Maybe it was him. It's a beautiful idea, I think. I love that. I mean, I must say, this is one of the reasons I got interested in science. This kind of idea, I think I heard about it when I was a teenager. It's so beautiful. I mean,
yeah, the universe is kind of narcissistic. It's
we're just the mirror that reflects it. And I did love that image. That's why when you said that, that's why it resonated very strongly there.
Yeah.
And so one other quick question, please, and it was about what you were talking about earlier on. When you were talking about objects and gravity, you were talking about the moon, and you gave a quick to illustrate a point. You were talking about the moon and the gravity of being close to the Earth and things, right? When you mentioned about objects, as in you drop like a stone into a pond, it causes ripples, yeah? And you said that the ripples would be like the gravity or the effect gravity has. Just to check for in my head here, but the ripples, so obviously in your analogy, water is, an object of its own, and we get a much better idea of how ripples work in there. But what is in this analogy, what is the water in this analogy? Is that the other gravitational bodies that have these forces? Is the force between other bodies?
Well, so I mean, the water is space-time itself.
Yes.
So that's the backdrop where everything happening. That's hard to imagine, but I mean, it's like we were all okay. So there's this book called Flatland. You heard about this book? So there's a book about two-dimensional people living just on a flat surface, and all they know is this two-dimensional world, and then someone can come. If someone lives in a three-dimensional world, they come and lift them up, and they have no clue what's going on. They're just leaving the two-dimensional world they know. But imagine if you're living in flatland, the waves would be like the flat space, the sheet where you're living is starting to crumble. The waves are propagating on there.
Yeah, but you can also visualize it inside space, I think, because that's basically how gravity waves were detected in the LIGO experiment. So because when a wave would come, if you would magnify it, so what you would see is like space, the geometry of space being distorted in different directions, right? That's the ripple.
Yeah, I mean, the LIGO experiment is this, you have sort of a V-shaped situation where you have lasers, very accurate lasers that are shooting laser rays, very far, like a kilometer or something in each direction. And then, this was set up many years ago. It was just waiting for gravitational waves to hit. And it was only a few years ago when they had the first detection. And what happens is, as Robert is saying, the laser, is detecting that in one direction, space is contracting, and in the other direction, space is expanding. And so that's what the wave is. It's a huge wave that is just passing through the Earth, and it's contracting and expanding in different directions. And it was really detecting the merger of two black holes far away in the universe, two black holes are merging and rotating around each other, and that creates very strong ripples in space-time, and those were detected by the LIGO experiment.
So in some sense, it's a bit like if there would be an earthquake, right? Where you would stand, you would see the world shaking, right?
Yeah,
that's like a gravitational wave.
Yeah. And I mean, the only way to be sure that, it was not an earthquake is that the LIGO experiment is really, you have two of them very far apart. So the only way for this to really be true detection is if both of these detectors are sensing the same thing at the same time.
Almost the same time, because they measured the speed of light.
Almost the same time.
And it worked out amazingly.
Yeah. So I just have to say that it's I have to leave now because I have to.
Yes, I also have to leave.
Kids.
I think.
So maybe it's a good time to round off.
Yeah, thank you very much for answering my questions.
Yeah, thank you, Daniel, Carl. I'm sorry that we didn't get to your questions. Maybe you can send me a question, and then I can maybe forward it. Tristan, thank you, Daniel, Robert.
Thank
for
you.
coming.
It was a lot of fun.
Thanks.
I hope you enjoyed it. We for sure had a great time, and that you answered our questions so well, and especially my dumb questions. But thank you.
It was fun.
I
It was
really
great. Okay, bye everybody.
Thank you very much.
Thank you,
Daniel, Robert, and Tristan.
Thank
Thank
you
you so much for coming.
Okay.
Bye.
See you.
Bye. See you.
Yeah, thank you everyone for coming. I'm sorry if we didn't get to your questions. Yeah, please send them to me. I can forward them to the speakers. And yeah, follow the club if you like discussions and guest speaker events like this. Follow Science Society, and we will have more rooms like this. We are actually booked until mid-June with every weekday having at least one guest speaker coming. So tomorrow we will talk about nano-optics and nanospectroscopy with Rupert Gilmeyer, about his nanospacer work. Then on Thursday we'll have Dr. Allahan talking about disease-specific gene signatures, about her Parkinson research. Then on Friday we'll have Dr. Sarwood from IBM in Switzerland. Talking about neuromorphic computing and new neural network design. And yeah, next week we'll have Dr. Abel. He's a really big professor in memory, and he will talk about this new mechanisms he discovered for long-term memory storage and improving efficiency of CO2 capture on next Tuesday. So we have a lot of room, so follow the club. And yeah, thank you so much for being here. And oh, Robert is still here. Thank you, Robert. Special thanks. And yeah, I hope we'll see you again or hear you again soon. And thank you, everyone. Bye.